So it's a pleasure to introduce this week's speaker. Ellen has just joined the Geography Department as an assistant professor and also series as a fellow. So welcome. She got her PhD in biostatistics from Harvard. But what's really exciting is that she got her undergrad from CU and worked at Earth Lab with us. Only a few years. So with that, welcome, and yeah, looking forward to learning more.
Thanks. Yeah, and thanks Earth Lab and Easel for having me. It's very fun being back, seeing some familiar faces and new ones. So today, apologies if you attended my job talk in March. This is very similar material because I think the slides are pretty well put together and address a range of different environmental health data science applications that I figured folks in here would be interested in hearing about. If I can progress slides. Great. So yeah, as Virginia mentioned, a little bit of background is I was in Earth Lab back starting in 2017, working with Colleen Reed when there was an environmental health wildfire smoke team. So I got my start in this field with epidemiological analysis and machine learning of wildfire air pollution in the Western US. So that was the tee up for all that has come after. Today, I'll be sharing about several projects that span a range of topics in environmental health, so air pollution exposure assessment, climate change and health, environmental justice, and this idea of policy design and evaluation, which is probably kind of vague for right now, but I will hope to make more clear as we go on. And then on the data science methods side, we'll be pulling from traditional statistical analysis all the way over to machine learning and AI, some causal inference, and also spatial and temporal analysis throughout, as we're familiar with in many environmental and public health applications. So to try and frame the three projects that I'll share about today, here are some broad questions motivating this research agenda. So in this arena of environmental health or climate and health, how can we transition from estimating effects to designing solutions? If you're familiar with environmental health, the field has historically been very focused on estimating the health impact of, say, a certain concentration of air pollution, certain temperature, and a certain, health endpoint. So the question here is, can we take that a step further to informing how individuals or institutions could make decisions in response to these environmental hazards? Within that, could we optimize limited resources for intervention across time and space? Could we adapt existing methods for settings with more limited or noisy data, which we see arising often in environmental justice settings? Can we critically interrogate and possibly harness big data science, machine learning, or AI innovations in this field? And can we advance the so-called kind of planetary health paradigm of thinking more holistically across different types of environmental exposures or hazards and different types of health or well-being endpoints? And while addressing, these various questions, we run into some ubiquitous complications, which many of you have probably encountered in your own work, social and environmental disparities or injustices, and then more on the method side, spatial and temporal dependence and confounding. So today, again, I'll be sharing these three projects, but I encourage you to keep in mind these framing questions to kind of see the connections between the topics. So the first project will be thinking about informing the design of low-cost air quality sensor networks with simulations. Second, optimizing issuance of heat alerts for public health with reinforcement learning, which is a branch of AI. And then third is a more applied statistics focus, quantifying air pollution from plastic waste export and burning with remote sensing and causal inference. So again, as you can see, all pretty different environmental applications and different types of statistical methods, but the framing questions of, how can we help individuals and institutions make better decisions is this kind of common theme throughout. A few notes also before diving in is for each of these projects, I'm giving kind of a high-level overview. I will not go into all the technical details, but I'm happy to follow up with you if you have questions later. And code for the first two projects is already publicly available. The third will soon be made available once we're done with revising the paper. So for each project, I'll feature one or two major collaborators, but of course with team science, there are a lot more folks behind the scenes. All of these were supported by this group at Harvard, led by the wonderful Francesca Dominici, called National Studies on Air Pollution and Health, but now they've kind of expanded out into climate and health. So if you are on the CAFE email list or GeoCafe, they're a research coordinating center for climate and health that publishes a lot of interesting news about various data sets or potentials for collaboration in the climate and health space. So if you're interested, definitely their email list is something to join. So let's dive in. First project. For this project, I had the pleasure of collaborating with Danielle Braun, a research scientist at Harvard, and then Priyanka D'Souza, who some of you might know if you're familiar with the air quality space. Yes, I'm seeing some nods. She's based currently at CU Denver. A bit of background motivating this. This is a map, at least back from 2021, of air quality data reported by countries around the world. And what we immediately notice is that there are huge gaps, right? Certain continents that have almost no air quality monitoring. And even if we were to zoom in on the United States, there would be plenty of places where people don't have a monitor anywhere nearby them. So in this project, we focus on California. So this is zooming in. The little black dots might be hard to see, but those are reference monitors deployed by the Environmental Protection Agency or California Air Resources Board. And the kind of pinkish purple dots are these locations of low-cost sensors that people or organizations have deployed to kind of fill these information gaps between. So this motivates the project in that low-cost sensors could potentially fill these kind of spatial information gaps between these reference monitors, and that has been referred to as democratizing access to air quality data either in the US or abroad. When I'm talking about low-cost sensors, these can go as low as about $250, whereas these reference monitors can be 10 grand or more, so quite a big difference in cost per instrument. But with this lower cost come more concerns about measurement error, noisiness in the sensor measurements. So one question we're trying to ask is, what's kind of the trade-off between having these, more accurate sensors versus, higher spatial density. Another just important framing point is that there's persistent air inequality or differential exposure between socioeconomic and demographic groups. And this 2022 study found that in the US, the discrepancy between groups' exposure has been increasing even as overall air quality improves. This particular study was also motivated by a past one that Priyanka had done with Pat Kinney, looking at the distribution of purple air sensors, which are the most common brand of PM2.5 low-cost sensors. And they found that these tend to be located in more privileged areas in the US. Just for context again, if you're less familiar with air pollution, PM2.5 fine particulate matter is the air pollutant that tends to be of most concern for human health when we're talking about health standards, health studies, et cetera. So Priyanka and her colleague found, these tend to be located in more privileged areas. And the question is, okay, if folks are potentially being exposed to more pollution and they don't have as much access to data, how could we think about maybe rectifying that? And back in 2020-21, when I was designing this study, at the time, both the Inflation Reduction Act and American Rescue Plan had allocated money for enhanced community air quality monitoring. And we're thinking about prioritizing environmental justice communities. So the question was, how could that type of resource best be spent? So let's dive in now. I've hopefully teed this up enough. The policy or decision-making questions we're trying to address here are, where should we place these low-cost sensors to fill gaps in the reference monitoring? And with thinking about this with respect to both accuracy and equity of air quality reporting. And if we think about having a budget for community air quality monitoring, what kind of improvement in reporting could we expect from deploying a certain number of sensors with a given accuracy? Translating this into more kind of specific research questions, we're looking at the distribution, density, and placement of these low-cost sensors, and we're thinking about what mechanisms are driving inaccuracy in air quality reporting. So what do I mean by these mechanisms? Here's a little diagram that I like. So if we think of this triangle as being a person or community of interest, and this square being a monitor sensor that's collecting and reporting air quality data, the background color here is representing the pollution level. If there's not an air quality instrument anywhere nearby you, it stands to reason you might not be able to get accurate information about your true exposure. A second scenario is even if there is, an air quality instrument fairly close by to you, but there's a lot of local variability in air quality, you might not be able to still get accurate information about your exposure. And then third, if there's sensor measurement error. So the device has some noisiness or error in it that is, again, kind of messing with the accuracy of the data. So one question here is, how do these mechanisms, both individually and jointly, affect this real-time air quality reporting? And we investigate this using simulations to compare different counterfactual scenarios. So an overview of this simulation approach is that we built the simulation closely on real data in California. We considered people's air quality information from their nearest air quality instrument, so either a sensor or a monitor, in terms of both the PM2.5 concentration and the air quality index, which you might have seen the little AQI diagram before, like on your phone, these different rainbow colors. And to make this hopefully a little bit more visualizable, here's this diagram. So if we imagine on this grid, these are maybe 1 kilometer by 1 kilometer grid cells. The background color again is people's true pollution exposure. We can think of, where'd my mouse go? This triangle being an EPA monitor and this circle being a low-cost sensor. On this side of the diagram, the color shown in the box is basically what is the information that people are shown from their nearest instrument. So the people my mouse keeps disappearing. In the purple are closer to this reference monitor, and the people in the orange here are closer to the sensor, right? That's all we're doing. And these red and blue X's are just showing whether or not people's information is misclassified. So people with red X's are being shown an air quality level that's higher than their true exposure, and vice versa for the blue X's. So then we can see what happens when we add in sensor measurement error at this low-cost sensor location, right? This distribution of what people are shown changes, and so does the distribution of kind of misclassified information. In addition to thinking about, discrete misclassifications, we could also just calculate mean absolute error between someone's real and kind of shown exposure. So that was kind of an illustration of within each run of the simulation. But using this, we can, place hypothetical kind of arrangements of low-cost sensors lots and lots of times using the simulations to kind of account for random sampling error. And we can think about prioritizing the placements based on different realistic strategies. For instance, putting them at schools shown in these blue dots, or prioritizing putting them near highways shown in the navy blue. California also creates this index called CalEnvirScreen that basically describes environmental justice, so indicating counties that both have a high exposure to various environmental pollutants and also maybe a high measure of socioeconomic disadvantage. So we can look at either the kind of aggregate CalEnvirScreen or the pollution component, which is shown in the kind of yellow-orange there. So with these simulations, the big picture idea is that we can characterize relationships between the number of sensors we're deploying, the spatial density, right? The noisiness of the sensor measurements, or that sensor measurement error, and these different placement strategies, including potentially prioritizing environmental justice communities. So I'm going to show you a couple different, of the plots we can get out of running this type of simulation. And to avoid becoming overwhelmed, I encourage you to let your eyes focus on the light blue lines, because we found that placing these sensors at schools ended up being a pretty good strategy. So what's happening in this plot is on the x-axis, we're thinking about increasing the number of sensors that we're deploying across the state of California. On the y-axis here is each individual's distance to the nearest air quality instrument, either a monitor or sensor. And unsurprisingly, as we deploy more of these sensors, right, that distance is decreasing. The different colors, again, are just referring to the different kind of prioritization strategies we use. Light blue lines, again, focusing on placing them at schools. And then the different solid dotted lines are just referring to whether we're calculating this metric for the population overall, or census block groups with a high percent of non-white residents or high percent of residents living in poverty. So this is just kind of a first intuition for what happens as we deploy more of these sensors. Let's now think about people's error in air quality reporting. Before getting there, I just want to note that deploying thousands of these sensors across the state of California is quite realistic. Even back in 2021, there were over 4,300 of these deployed across the state, which, if we had extended this plot outwards, would have dropped their average distance to the nearest monitor sensor down to about 2.5 kilometers. So it's a busy slide, but now what I'm showing is on the y-axis, the mean absolute error now between each individual's real exposure and what they're shown from their nearest monitor or sensor. And we're not in a setting yet with measurement error at the low-cost sensor locations. And what's kind of intended to be shown here is the patterns on this plot are very similar to the patterns on the distance plot, right? Unsurprisingly, your kind of error in air quality reporting decreases as we increase the number of sensors. And for a bit of scale on the y-axis here, the mean absolute error is around 1 microgram per meter cubed, and the annual national ambient air quality standard for PM2.5 in the US is 9 micrograms per meter cubed. So this is a reasonable amount of error in people's real-time information. So now let's think about what happens if we turn the knob, increasing sensor measurement error, right, at these low-cost sensor locations. We can first look at a scenario where we look at an empirical distribution of measurement error using this kind of calibration equation that EPA researchers developed. And the kind of big takeaway here is before the lines were downward sloping, now the lines are upward sloping. The extra noise at these sensor measurement locations is now overwhelming the value of kind of being able to get more measurements across space. Whereas if we kind of manually change the amount of measurement error, we can see different places where some of the strategies might be beneficial, others less beneficial in terms of where we're placing these. The big takeaway is that we can, using these simulations, tweaking all the dials, we can identify optimal low-cost sensor placement strategies and performance as a function of this device measurement error. So zooming out to overall contributions, we attempted to create a novel and easily modifiable methodology that kind of uses a decision science framework and is trying to really emphasize policy relevance or usability. With this, we were able to quantify the impacts of these low-cost sensor network characteristics and hopefully increase understanding of those kind of mechanism interactions, the distance, local variability, and air pollution, sensor measurement error, and also the language that we can use for describing those trade-offs. Ultimately, we did make recommendations that placing the low-cost sensors at schools would be beneficial, and also made recommendations for these kind of measurement accuracy requirements to inform future calibration approaches that either engineers or other scientists working with these sensors might use. Even bigger picture is that this type of methodology could be adapted for other kinds of environmental monitoring or policy objectives that we might be interested in doing. All right, realize I'm kind of zooming through. This is, again, just to give a bit of a sampler of types of environmental health decision science that I've been thinking about. So moving on to the second project is thinking about heat alerts and reinforcement learning. And for this project, I collaborated with Mauricio Tech, who is currently a research scientist at Amazon, was previously a postdoc at Harvard, and Greg Wallenius, who some of you on the call know, at Boston University School of Public Health. So the decision-making questions at play here are, when should we issue heat alerts? Before we were talking about, where might we place low-cost sensors? Now we're talking about more the temporal aspect. When should we issue heat alerts to trigger health protective actions, either for individuals or institutions, and in a realistic context of limited resources? And, can we gain intuition on where heat alerts are most effective? The specific research questions we're looking at are, can reinforcement learning, which I will introduce in a minute, be used to optimize heat alert issuance in this context of finite resources? If not, what modifications could be made to enable this? And again, what mechanisms are kind of underlying the performance of RL in this setting compared to the actual National Weather Service practice? So I'll also share a little bit of background work on heat alert optimization to motivate what we're doing. In 2023, a paper developed a causal inference technique for stochastic interventions to infer whether increasing the probability of issuing a heat alert would be beneficial. So basically asking, if we increased our likelihood of just sending more alerts over the summer, would that be beneficial for health? And second, a more traditional approach to thinking about this would be to try and identify localized thresholds above which heat alerts should always be issued. So a relatively simple threshold-based policy would be, if we identify our threshold is 101 degrees Fahrenheit, then every time the temperature goes above that, we issue a heat alert, is the idea. And the gap that we're addressing in this project is that none of these past approaches addresses the complication of what's called sequential dependence. And what this means is that if I issue a heat alert today, might that impact the effectiveness of a heat alert that I issue tomorrow, next week, etc. And this is a well-known phenomenon in mobile health and other applications. In the heat alert setting, we kind of expect that sequential dependence might be at play due to two somewhat related factors. So first is this notion of alert fatigue, which again, I see in mobile health commonly. The idea is just as we send people more and more notifications, eventually they'll stop paying attention. And related to this is that both individuals and institutions might have limited resources to deploy precautionary measures. So if you can imagine, maybe someone has the ability to take off work one day if it's, really, really, really hot and they work outside, or change the way that they're, going to work, and they aren't able to do that. The more and more days have heat alerts, or a municipal government might have a limited budget on how many days in a summer they can open a cooling center and staff it, right? So that's this notion of kind of cost constraints. So now what is reinforcement learning? This is a rapidly expanding field of approaches that was created explicitly to deal with these types of sequential decision-making problems. That's a mouthful. It has shown success in a variety of fields ranging from robotics to mobile health. And I actually even know some folks in CO engineering who are using this in the realm of power grid optimization. The general idea is that an algorithmic agent is using a policy, in our case, when to issue a heat alert, to interact with its environment, which I will describe in a couple slides, to either maximize a reward or minimize a penalty. So in our case, we're trying to minimize adverse health outcomes like deaths or hospitalizations. Here's a little visual for those of you that like this. So if our agent is deciding when to issue a heat alert, that's interacting with this environment. The environment is then returning information to the agent about kind of the observed rate of these health outcomes, and also information about the next state at which the agent will need to make a decision. And this falls under kind of the machine learning AI umbrella because the policy under the hood is learned using neural networks. So it sounds all well and good, right? We were able to, formulate heat alert decision-making in the context of RL. We should be able to just press go, right? As we know in research, that's never how it works. So some of the major challenges we encountered, they all fall under the umbrella of standard RL methods, basically not being built to handle these real-world complexities that we encounter all the time in environmental sciences and public health. So the first is low signals, small and relatively easily confounded effects in observational environmental health data sets. Second, which I assume many of you are familiar with, is spatial variability here in the heat alert health relationship, which could be due to factors like geographic self-selection, climate adaptation, socioeconomic status, environmental co-exposures, etc. And then third, this notion of a limited intervention budget due to alert fatigue or cost constraints. And one note I'll make on the third part is that This also allows us to directly compare with the observed National Weather Service behavior, basically by saying, okay, we're holding the number of alerts equally and just thinking about when could we have basically better distributed these for greater impact. So we propose a framework to address those challenges, first creating a realistic environment or simulator, which I will introduce on the next slide. But this basically allows us to train and evaluate reinforcement learning or other counterfactual policies that we might propose and compare them to the observed National Weather Service policy. And then second, we can use that simulator to run RL and hopefully dig into the results and provide domain relevant insights. So why do we need this thing called an environment or simulator? This isn't something we traditionally need in applied statistics or epidemiology. The motivation is that the RL agent needs to be able to explore what happens under different counterfactual scenarios to learn how the system dynamics work and ultimately determine its optimal decision-making policy. And the way to think about this is that a lot of RL algorithms were developed in the context of video gameplay, right? Where you have some sort of video game simulator, chess, Atari, whatever, and the RL algorithm is able to interact with it a whole bunch of times and figure out what kind of strategies it can use to optimize the number of points it's getting out at the end, or whether it wins at chess, right? So that's how a lot of these algorithms were developed. The problem is in our setting, there isn't some sort of like environmental health simulator handed to us. We actually have to create it using real data. So in this context, instead of trying to maximize points in a video game, we're defining the reward, what it's trying to maximize, as a cumulative reduction in hospitalizations based on real Medicare inpatient data. And as a reminder, Medicare is referring to healthcare for folks 65 years and older in the US. So within this environment, there are two kind of components. The first component is a rewards model where we're basically just specifying relationships between the weather, right, heat, when we issue heat alerts, and then observed hospitalizations in Medicare. And for those of you who are interested in the statistical approach, we used a Bayesian hierarchical model to model this, and we allowed the system to vary by time as well as location. One other thing for any health scientists in the room is that we had to really carefully specify the outcome of interest, the specific hospitalization codes we were looking at in the simulator, because of this kind of interesting causal pathway issue. So we're interested in this setting in the pathway of us issuing a heat alert, people or institutions taking some sort of protective measures, and that reducing the risk of people being hospitalized, right? But unfortunately, there's also maybe this other pathway where people see a heat alert and they become more aware of symptoms that are already occurring either in themselves, a neighbor, a family member, etc., and that increases their risk of going to the hospital. So RL would not really be able to disentangle this in the data if we didn't carefully just look at a subset of hospitalizations. So we are separating what we're calling kind of obviously heat-related hospitalizations that have shown to actually increase on heat alert days, such as dehydration or heat stroke, versus what we're calling these not obviously heat-related hospitalization types that have been shown to be associated with extreme heat in Medicare. But your average person off the street probably isn't going to think, oh, diabetes mellitus related to extreme heat. So that was the rewards model. The second part of this is what we call the transition model. And this is basically just getting at if we're sending the RL agent a sequence of days or states at which it has to make a decision whether to issue a heat alert, we have to characterize that basically sequence of days and the kind of characteristics on each day. So a traditional RL approach would be to develop a probabilistic model for this. In our setting, the kind of key observation we made is that this can be decomposed into the exogenous and endogenous components. Endogenous just basically being the things the RL agent can control, which is just the history of when it issued heat alerts prior to this. In the heat alert setting, most of the interesting stuff that's happening in the environment is out of the agent's control. It's exogenous. The RL agent issuing heat alerts has no control over the weather, right? Which is kind of the key dynamic driver of this system. So here, rather than potentially introducing error being trying to model the weather probabilistically, we can just sample the real observed historical weather trajectories and feed them into the environment that goes to the agent. And to avoid overfitting on a finite number of these trajectories where we have the paired weather data with the heat alert history data, we can potentially augment with sampling weather from other counties in the same regional climate zone. So this altogether is the RL environment. If you're interested in learning more about this, it's public available in a Python package, Weather to Alert, so folks can experiment with different RL developments using the environment or any other type of policy that you might want to propose and run through it. But in this project, we created the simulator. We then tried running RL. As I kind of teed up before, RL out of the box isn't really built to handle this sort of scenario, both because we can't issue too many heat alerts to run into those alert fatigue or cost constraint issues, but also heat alerts just only make sense on very hot days. And that's a sort of intuition that we would, of course, have as humans, but the RL agent would not know right out of the box. So for this, we made two very simple modifications to constrain RL during its optimization. First, strictly limiting the number of alerts in each summer to that was actually issued by the National Weather Service, and then also restricting issuance of alerts to very hot days. So in contrast to the kind of simple threshold-based policies I mentioned before, where whenever the heat goes above our threshold, we issue alert, here, we're just identifying a threshold below which it's not allowed to issue out an alert. So above the threshold, it can decide which days to issue the alert. And that is identified empirically. So here's a little bit of a visualization just for one of these counties in the year 2015. So moving across the x-axis are the days of the summer season that we were running these models. The black line is the quantitative heat index that was actually observed in the summer. And then these different colored dots are the different kind of days on which each of these different policies decided to issue a heat alert based on different algorithms. So the gold is the actual National Weather Service policy. The ones down here are the different RL policies. And one thing to just note here, I'm happy to chat more with folks at the end, is that some of these policies are actually stochastic, so they don't issue the same exact trajectory of heat alerts given the same inputs, which is why we're showing a couple different lines of the pink and green dots. So we basically did this constrained RL optimization separately for each of the counties that we were looking at. We implemented that alert budget, the heat threshold, this RL agents interacting with the environment that we talked about in the first stage, and we're getting out a whole bunch of results across the different counties in the US. So a question is, looking into these results, how can we interpret them? How can we interpret the performance, where it's performing better or worse than the National Weather Service currently? So we did this, in technical jargon is contrastive explanation, but it's basically just running a classification and regression trees to predict, where the RL policy performs better or worse than the National Weather Service using characteristics of the counties and also characteristics of the policies that it learned. So zooming out, having talked about all those different steps, what did we learn from this project? First, that standard widely used reinforcement learning methods perform worse than the National Weather Service in this data-driven simulator that we created. But we can implement these relatively simple modifications like a quantile heat index threshold, and then the RL is able to outperform the National Weather Service. For a bit of a context, our estimate is that we could save about 300 of these not obviously heat-related hospitalizations per year under 2023 Medicare enrollment, which probably does not sound like a large number of hospitalizations, but the thing to keep in mind is both that issuing the heat alerts themselves is a pretty low-cost intervention, right? And then also we're just looking at this pretty small number of hospitalization types in the Medicare population. We could potentially estimate much greater impacts from these heat alerts if we were to consider, a wider range of health outcomes or, also different age groups. But, even though we saw this kind of overall improvement from, deploying the RL in our simulator, there was this large heterogeneity across counties. Some counties did not benefit from this relative to what the National Weather Service is currently doing. So deploying that post hoc analysis with CART, we found that RL tends to perform best in counties with one of two characteristics. First, counties that tend to experience more prolonged heat waves, which can be associated with being in a more humid region. And our intuition here is that more simple kind of threshold-based policies, such as the ones that the National Weather Service is currently using, when they hit a heat wave, just tend to issue a whole streak of alerts, right? Which is more likely to induce alert fatigue in the population. Whereas it seems like RL is better able to maybe identify that alert fatigue signal in the data and choose to not send as many heat alerts in a row to tire people out. The second characteristic was counties that had higher alert health signal in a rewards model, which basically meant that, on a heat alert day, you saw a greater reduction in hospitalizations. And unfortunately, this is associated with higher socioeconomic status, which actually, our tuition within public health is that, folks of higher socioeconomic status might have more agency or resources to respond to a heat alert. Maybe they have access to air conditioning, maybe they have access to, working from home, whatever it is. But just, when thinking about deploying a AI enhanced alert system like this one, thinking about how we can maybe offset, which counties are benefiting more or less from a system like this will be important. So zooming out to overall contributions, we developed an RL framework for environmental health applications. and identified these kind of modified RL policies that could outperform current heat alert issuance and tried to provide somewhat intuitive explanations for why that was occurring. We published our realistic heat alert simulator and broadly tried to kind of establish a bridge between the environmental health and artificial intelligence fields, identifying some of these common issues that we encounter. More broadly, this methodology or something like it could be adapted for other kinds of environmental exposures, health and well-being outcomes, and different types of budget constraints, either kind of manually specified or learned from the data. One caveat I will mention is that having gone through this whole project, it took almost like 2 years, I think, from the design phase to the actual publication. I have somewhat mixed feelings about the computational demand for this. The kind of argument from the RL side of things is that you could train a model once and then basically just update it with new data as you go, which is less computationally intensive, right? Updating it. The idea is that this kind of could be deployed online, so you wouldn't have to do the whole large training multiple times. In practice, my experience was that you had to kind of run these things with a whole bunch of different hyperparameter configurations, which was pretty computationally intensive. And then in practice, folks would probably want to update the whole model more frequently. So it's kind of an open question in my mind of whether there needs to be some sort of update to this to make it more computationally efficient, or compare, the types of policies that we got using RL and the kind of intuitions we got there to inform maybe some less computationally intensive, but potentially more effective policies. So anyway, that's something I'm putting out into the universe. All right, so switching gears into our last project, and I think I'm doing okay on time still, is this applied statistics project thinking about quantifying air pollution from plastic waste export and burning with remote sensing and causal inference. So a bit of background for this is that a 2024 Global Health Review stated the open burning of plastic waste is an urgent global health issue. An estimated 40 to 65% of total municipal solid waste is currently openly burned in low and middle income countries. And our goal in this project was to facilitate large-scale policy impact evaluations. The specific case study we're focusing on is that, as you might recall, in 2018, China banned the import of plastic waste. And for context, between 1988 and 2016, they were receiving almost half of global plastic waste exports. So when they shut their borders to this, the rest of the world very quickly had to figure out what they were going to do with all that waste. And unsurprisingly, a lot of other countries in the Southeast Asia Pacific region started receiving an influx of this. So in 2018, Indonesia became a net importer of plastic waste. And in general, as many of you know, export of waste, not just plastic waste from high to low income countries, is a major environmental justice concern. I also want to mention just a couple connections with climate change that might be less readily apparent. Plastic production is actually a major driver of climate change. I was shocked to know that the plastic industry is responsible for 4 times more greenhouse gas emissions than the airline industry. 99% of all plastics are made from fossil fuels, and this has led to plastic production being termed the fossil fuel industry's plan B if the world is successful in moving over to renewable energy. And the OECD estimates global plastic use will or could triple by 2060. The slight optimistic thing is that a global plastic treaty is currently being negotiated at the UN, which could help to reduce the amount of plastic pollution being generated. Unfortunately, as with many international approaches, progress has been slow. I think they've been having intermittent negotiations since 2022, so TBD whether this actually materializes in any sort of treaty. But going back to the specifics of this project, the policy questions of interest are, did air pollution increase in Indonesia as a result of this influx of plastic waste they received after China was no longer accepting it? And we're interested in air pollution via the mechanism of trash burning. And if there was an effect, was there variation that we can characterize across the country? For research questions, can we credibly estimate an effect, if there was one, without ground level air quality monitoring using only remotely sensed data projects? And to contextualize this, so this is going back to the plot that I showed in project 1, and this pink box, it might be a little hard to see, but that's outlining Indonesia. And basically there are only like 2 sensors or monitors within the entire country. In 2021, back when my study period started, there actually weren't any stable air quality monitors in the whole country. And to my knowledge, the 2 that we're seeing are both in the capital city of Jakarta, one on the US Embassy and the other on the ambassador's home, which to my knowledge, no longer are running. So if, again, there's an effect, we can identify this using remotely sensed data. How could we characterize the spatial variation? So for this project, I did some data sleuthing, which was kind of fun, also a little frustrating at times. But I pulled together some different kind of more standard environmental variables, such as PM2.5 air pollution based on aerosol optical depth, meteorological covariates from ERA 5, active fire points from VIIRS, which I know many folks in this room have used, And a more kind of novel variable that I created was an index on proximity to port activity. It turns out that cargo ship signal density is also a remotely sensed data product. So we can look at the density of cargo ships loading around the coast of Indonesia, create basically an inverse distance weighted index of this. The other data set I was very excited to find was one that's created by this organization called Global Plastic Watch that used machine learning on satellite imagery to identify sites where there are these large open dumps of waste. And their API also provided some additional covariates like population estimates nearby each of the sites. So to kind of look at feasibility of a study like this, I did just some basic exploratory data analysis and overlaid these active fire points over the open dump sites identified by Global Plastic Watch and saw this time series aggregated across the sites. So up until 2018, we kind of see some of this seasonal variability. And then, after 2018, we're seeing this large increase in fires at these open dump sites. Seems like kind of a classic pre-post setup. So that motivated me to then dig into this further using causal inference methods. So for those who might be less familiar with this kind of more econometrics way of thinking about science, here's a brief intro. So difference in differences is a very standard quasi-experimental causal inference method. And the general idea is that if we have time on the x-axis, there was a policy that was implemented at this specific point in time that creates a pre-treatment period and a post-treatment period. On the y-axis, we have some outcome of interest. In our case, it would be air pollution. And the idea is that you have both a treatment group who experiences the policy intervention and a control group that does not experience the intervention, but is similar enough to the treatment group that over time, we would assume they have basically parallel trends in the outcome in the absence of treatment. And that allows us in the post-treatment period to decompose basically the difference between the two into this constant difference between the two groups and the treatment effect in the treatment group. So that's standard difference in differences. There are a couple complications that we run into in this setting. So what do we do in this sort of setup if the pre-post or treatment effect varies by location? So for instance, you can imagine there's a different effect observed in cities and in rural areas. So you could imagine kind of estimating that as a function of population density. And second, what do we do if there are no reasonable control locations to kind of create this control group because all comparable areas that we could otherwise use to create a control group were similarly affected by the policy? So a lot of folks encountered this in the context of trying to look at the impact on air quality of COVID-19 lockdown, where lots of cities kind of did lockdown around the same time. So it wouldn't be straightforward to compare city A to city B because they both experienced the policy. One other note before diving into the methods that we actually used, this is a map of all of those open dump sites across Indonesia, and then the color is the port proximity index that I created. And just for further kind of motivating the statistical methods, we expect the long-term trend in air pollution at these dump sites versus just any other sites, what I'm referring to as non-dump sites. We expect their long-term trend in air pollution to be different because the dump sites, in addition to potentially receiving some of this imported waste, are also receiving an increasing amount of domestic waste generated within Indonesia. And we know that a lot of that domestic waste is openly burned, right? So we might imagine that the air pollution, even in the absence of China's ban, would have been increasing at these open dump sites. So we have to think about kind of, the impact of that versus if we're trying to estimate the impact attributable to China's ban. So for this project, we kind of merged these two relatively new strains of causal inference. The first was a paper estimating a heterogeneous pre-post, the difference in differences policy effect, using distance as an induced continuous exposure. So this is getting back to the idea of estimating that kind of treatment effect as a function of some other variable. And a second strain uses pre-intervention years as controls for post-intervention years. So instead of trying to identify some separate control locations, we're basically saying, okay, our locations are fixed. Let's just look back in time before the treatment happened and use those as controls for the post-treatment years. And this, again, was an approach that a lot of papers took looking at air pollution impacts of COVID-19 lockdown. So we combined these two, and we also extended the uncertainty quantification in one of them to account for residual spatial correlation, which again is something that we see all the time in environmental science and public health. So a little bit of data and notation is that we're trying to estimate what we're calling the average dose effect on the treated. If you're familiar with causal inference, you've probably heard of the average treatment effect on the treated, or ATT. All that means is that we are looking basically in the years post-China ban, and within that, we're trying to estimate the average difference in Y, our outcome, monthly PM2.5, between a scenario where this, Y1 is where China does implement its ban versus a counterfactual scenario where China did not implement its ban, that's the Y0. And we're trying to estimate this as a function of this continuous dose metric, which in our case is this proximity to ports index that we created, right? So we're trying to estimate this difference in PM2.5 China ban versus no China ban as a function of these sites' proximity to ports. And then, yep, B is our time period indicator I already mentioned. Under the hood here, when we are estimating this effect, we are accounting for covariates like meteorology, population density, presence of wildfires, etc. Okay. A couple more technical notes, just again, for those who might be interested. So one of the papers that we were basing this and kind of modifying this method off of proposed this technique for multiply robust estimation. You probably heard the term, if you're familiar with causal inference, doubly robust. The intuition here is that we can combine output from what we call an outcome model, where we're predicting air pollution, and a propensity score model, where we're predicting our exposure, in this case, the port proximity. And the idea is that by combining output from both of these models, we're kind of protected from misspecification of either model. So if either model kind of misidentifies relationships between variables, we still have the other model to kind of rely on, is a bit of the intuition here. And a very technical note is that here we actually have 4 models, for our basically post-treatment outcome, pre-treatment outcome, and then we have propensity scores both for our, again, binary, kind of the policy was implemented here, and also our continuous exposure. Overall procedure for this, just again, indication a lot of stuff is happening under the hood that I'm not really getting into here. We can estimate these kind of, what we call nuisance function models using machine learning for flexibility. We can plug these into an equation that is kind of specific to the effect we're trying to identify. We perform some kind of final kernel regression to get our final effect curve out. Again, technical details. If you're interested, you can read the paper or come talk with me later. Here is the type of result that we can get out through doing all of those complicated steps. So on this plot, this is our main result. On the x-axis is our port proximity index as a quantile. So the density basically of observations is constant across that axis. On the y-axis is our average dose effect on the treated, basically just saying what is the difference in PM2.5 in the scenario where China implemented its ban versus it did not implement its ban. And so we can see in these curves, I encourage you to focus on the red line, which is our multiply robust kind of, outcome or result that we're focusing on. The interpretation here, looking at the confidence intervals, is that we see, a statistically significant increase starting around, this port proximity index. And at those levels, the effects can range between about, 0.75 to 1.72 micrograms per meters cubed, which, if you're familiar with air pollution, is actually quite a large concentration difference. It's 15 to 34% of the World Health Organization's recommended annual limit for PM2.5, or about 5% of the pre-2018 average at these sites. One other technical note I will make is this box highlighted in green is the one I showed you before as our main result. This is basically just showing that incorporating or accounting for residual spatial correlation in these confidence intervals is important. If we had not done this, the confidence intervals would have been much narrower, and we think probably erroneously so. So zooming out to contributions, I will note again, this paper is under revision at a stats journal where they give you lots and lots of little itty bitty technical details that we're still going through. So the results are subject to change slightly, but there's a preprint on arXiv if you're interested in seeing the kind of preliminary version. So in this paper, we quantified the increase in air pollution at these open dump sites in Indonesia due to the burning of increased plastic waste in the wake of China's 2018 ban. It's a mouthful, but hopefully after seeing this part of the talk, you know what I mean. To do this, we combined these 2 strains of causal inference and also extended the uncertainty quantification approach. And in general, developed this multiply robust approach to estimate the impact of a large-scale plastic waste policy on air pollution in a setting without access to ground-level monitoring data, which is quite different than a lot of studies that have attempted to do something similar in the past. In general, this methodology could be adapted for other kinds of environmental policies or natural experiments, such as natural disasters, in settings with limited data. So the intuition here is if you have some sort of event or policy that happens at a specific point in time, and you're interested in estimating the effect as a function of some continuous factor, this is the type of method that you could use. So I know I just went through all those projects pretty fast. Let's give just kind of brief overview of where we've come in the last 45 minutes or so. So we talked about different areas of focus in environmental health, different areas of data science methodology, these 3 different projects, the low-cost sensor simulations, heat alert reinforcement learning, plastic waste burning causal inference method. So looking ahead, I also wanted to share just a couple thoughts. If you're interested in collaborating, you have an idea for extending one of these things, or talking with me about, ways to bring in some of these environmental health data science ideas into whatever you're working on. Some possibilities I thought of were folks might be interested in identifying areas that would benefit the most from an environmental intervention, potentially accounting for existing health inequities or multiple exposures. So one thing that actually a lot of papers have started doing now is trying to think about, if we were to optimize prescribed burning locations to minimize future health impacts of wildfire smoke, we could think about, adapting some of these methods to do something along those lines. Another possibility would be selecting other novel combinations of remotely sensed data to enable this kind of quasi-experimental evaluation of the social or health impacts of an environmental change or policy. And third would be integrating multiple kinds of climate-related forecasts to guide potentially multidimensional environmental alert issuance for health. So if we were interested in thinking about, okay, extreme heat plus wildfire smoke impact on some health outcomes, we could maybe think about adapting that sort of reinforcement learning approach too. So with that, I'm including my contact information here if you want to get in touch. Thank you all for being here and listening. All right, and I think we have some time for questions. So yeah, open to questions. Yes.
Thank you for your presentation. So in the third project, you mentioned that you include relation entity in the developing place. But I'm wondering if you also include income level. So Indonesia has exponentially increased their economic growth rates, and it means that they export and import more volumes in addition to the plastic waste at the port level. So without such income level variables, these results may be biased over the years.
So yeah, it's a good question thinking about, could you potentially have some sort of unmeasured covariate that could also be affecting the curve? And the intuition here is that because we're accounting for change over time, we're also accounting for long-term trend as one of our covariates. Unless there's some sort of shock that occurred at around the same time as our policy, right? Late 2017, early 2018, then theoretically, if there's some sort of gradual increase or even steep increase in income over these years, and we were looking, I think it was 2011 through 2019, then our kind of longer term time trends would already be accounting for that and averaging over it in the models where we were predicting things like air pollution and that sort of thing. So unless you're thinking that there was some sort of, say, policy implemented that also would have resulted in kind of a jump, right, around the same time as this 2018 policy, then the idea with this quasi-experimental causal inference setup is that those other factors that are kind of happening in the background, even if they're changing over time, we would be able to account for. Does that answer your question?
Yeah. So in other words, I'm wondering you also checked on parallel trends, and then is it satisfying?
Yeah. So that's details, again, that I totally glossed over here. So common in the difference and differences quasi-experimental space, you can do basically if you were to set one of the other years, right, other than 2018 as like our treatment year, you can test whether we also observed an effect, say using 2017 as our treatment year or 2016. And yeah, all of those we see, no significant increase in the effect in those years. So yeah, parallel trends, absolutely good to test for. Definitely stuff we've thought about. Yeah, great question. So thanks. I'm also looking in the chat if anyone online has questions. Yeah.
Results. So I might not be interpreting this right, but it seems like you're looking at the dose as like the distance from ports, right? Is that kind of your dose?
Vaguely, yeah. It's an inverse distance weighted that kind of accounts for the density of cargo ship loitering, but yes, basically distance.
Okay, and were you expecting that sort of the opposite relationship, the closer the ports, the higher increase in 0.5? Than what you actually done, or could you explain that a little bit more?
Yeah, good question on the interpretation. So what we see is that over here where the lines are crossing zero is low port proximity index. So they are not close to ports. We would kind of expect, right, like that there would not be an effect over here. What I thought you might have been asking about is like, why do we see this flattening off and even slight decrease over here at these high levels of port proximity? And our intuition is that a lot of these places where you have higher port proximity are maybe in bigger cities where there's more oversight. So folks might not, even if they wanted to openly burn, there's like more kind of forces in the government level or whatever preventing them from doing that. So that's why we think there might have been the slow kind of, tapering off or even decrease towards the end. But yeah, generally this is the expected shape where at low levels of port proximity, we don't see an effect. Anything else? Oh yeah, Jennifer.
Mine's like a little bit outside the specific
Sure.
results that you have here, but like given that you've kind of had this trajectory through environmental data science from undergrad, postdoc, now faculty member, like what are some of the things that you think we all need to be thinking about in terms of what's on the horizon for environmental science? So that was one question. The other question was, I was keen to hear about your commitment to open science and kind of how, like, I noticed you're like, oh yeah, this code's available, this archive holds this preprint, and your GitHub site is open and publicly available too. So I just was curious kind of what your arc has been kind of through and your commit, like where that comes from, your commitment to open science.
Okay, well, I think the second question is probably a little easier to answer. I learned a lot from being an undergraduate, environmental health data science intern in Earth Lab, where, I attended GitHub workshops. I heard all the time about open science and definitely, drank the Kool-Aid and continued with that. And certainly found that, yes, even, across various academic institutions around the country or the world, like I think that is the trend, is even more open science. The challenge in the environmental health or public health space is that often, we're using health data that is not publicly available. So in that sense, you have to be a little bit, or treat things a little bit differently than we would in environmental data science, where all of the data sets theoretically anyone could access. So in the case of, say, the heat alert reinforcement learning project, I was using Medicare data that, that senior PI, Francesca Dominici, pays for access to. That's a pretty rare thing to be able to access. So our kind of compromise there was that we, obviously could not make accessible the underlying data that we used to train the rewards model in that simulator, but we did publish the simulator so people can then kind of use the output of it. So I think in environmental health, we have to maybe find ways to compromise between having it be fully reproducible down to the kind of, very highly protected health data to more like what are these individual stages at which we could share the code or the, intermediate tools. So that's one thought there. But in general, I would say that, yeah, the world has continued moving even more so towards open science. And I think, everyone in my graduate program, whenever they published it or whenever they finished drafting a paper, would just put it on archive as an immediate thing that I think is both good for open science and also good for career development. Again, depending on your field, like stats journals are notorious for being, a year or more between when you submit a paper and when it actually gets published. So having something also out in the world is a way of saying, hey, I did this work. It's just very slow going in terms of going through revisions and publication. So for both of those reasons, I think publishing code and preprints are good. I'll also say in the case of the third paper, this was, method was adapted off of a project that a biostat student at, I think it was Penn, did, and it was partially because he made his code repository publicly available that I was able to kind of spin this up, make the, methodological changes that I wanted to, and do all of this, I think, in about a year, which otherwise would have been a lot harder for me to kind of, become familiar with the methods and update it. So certainly I am a proponent of open science. With respect to your first question, definitely a broader one. I will say it's been very interesting, especially being in the lab that I was during my PhD. For context, it was a little bit of an insanely large lab. I think at one point I counted they had like 12 postdocs. It's like kind of crazy, but similar to, in size to Earth Lab, I think. That group has in some ways, I think, been hedging their bets in terms of thinking about AI, also thinking about more traditional kind of, causal inference, statistical analysis, and maybe even looking at the environmental impacts of AI. So to my knowledge, they have one team that's trying to develop a foundation model for climate and health, and another team that is estimating the air pollution impacts of deploying, the data centers, right? So they're kind of looking both directions. And I guess that does, I tend to think they're well informed and thinking strategically about these things. So I think based upon, again, the AI stuff is all new in this field, but my sense is there will continue to be opportunities both for folks who want to kind of dive into the newest cutting edge AI, machine learning, whatever it is. And that world, of course, moves really, really fast. The computer sciences are just used to staying on top of kind of the new developments so much faster, I think, than a lot of us, statisticians or earth scientists. So I think for folks who are interested in that stuff, there will be opportunities for developing more of like the geo or spatial versions of a lot of those types of tools. On the flip side, I think there will also be room for those of us who are interested in thinking about, how do we use pretty well-established methods, but thinking about how to apply them in messier data settings in more policy relevant contexts, actually being, someone to talk with policymakers, talk with communities. Like, I think that translational aspect also, in my experience, it's very hard to be both like a true like cutting edge AI person and also like a fully community engaged environmental justice person, which of course is another, argument for team science, but kind of figuring out, I guess, in this interdisciplinary space, like where you want to sit on the spectrum seems to be, honestly, it's something I think I'm still figuring out for myself. But I feel like that's maybe a question to think about as you're developing as a young scientist, is like where on the spectrum from translation, community engaged work over to kind of the biggest models and the, kind of most cutting edge computer science stuff that you're going to be able to publish in like comp sci journals you want to be. I don't know if that really answered your question, but certainly I think the big picture thinking it's important, and I think an ever evolving process.
Yeah, no, it's great. I loved hearing your perspective. And one thing that I loved about your data harmonization too is like how you creatively put together different pieces in the last study that you presented on. And one thought that I've had too is like, what's the role for using large language models to generate environmental health data, because it's a sidestep around the protected health.
Oh, you mean like synthetic?
Yeah, so like, is that something we need to be aware of or thinking through of like, okay, how can we create data, not necessarily synthetic, but like say the smoke exposure example, like using Twitter and smoke mentions as proxies for like how many people are potentially exposed, as opposed to then having to rely on like hospitalizations and hospital visits, which might be harder to access. So do you see that frontier happening in the future?
Yeah, I think, as you said, this was a project where I had to be a little bit more creative about, okay, they don't have this ground level exposure. Can we use the remotely sensed proxies? And yeah, I think in settings where, health data is either inaccessible or just so expensive or has, some sort, it's private, whatever. I do think there is room for being creative with kind of what you're using as proxies. Of course, then if you're using proxies, you have to think about, okay, what are the potential, kind of sources of measurement error? Could there be bias in some way, right? Like you're going to get a lot more pushback. And for instance, we have in this paper with, are you, leaving out some sort of important unmeasured confounder, right? Like, have you fully thought through? And I think that's maybe where some of the causal inference or like more mathematical approaches come into play also, is the more kind of messy in some sense your data is, the more pushback you're going to get, and the more rigorous I think those methods have to be to kind of counterbalance it. So yeah, it's really a good question, and one that I'm continuing to mull over too. Yeah. I think I saw a hand. Yes.
That wasn't a question, but I wanted to note that we sort of opened up the session at noon as sort of a meet and greet so that people can stay and chat. There might be some other people coming that didn't come to talk, but were available for that chat. So I just want to note people when I start poking the head of the door, we should invite them in if they do. I think this follows on Jennifer's question around, but really around reframing of EJ studies. I feel like there's, so that's.
Oh, I also see there's a raised hand online, so we'll get to, that too.
Yeah, I think I'll ask this question to you in a different setting. So go ahead and go to that.
Okay, sure. Online, Wantong.
Yes, I do have a few questions, and but first, thank you very much. Very interesting talk, and I really enjoy all what you said before. My quick question is related to the causal inference, either using machine learning or not, because currently I see most of your studies might focus on like figure out which policy has certain impact, taking the causal inference. But in my own kind of domain, I'm more like forest management and understand how that could provide sustainable function to climate mitigation. So for forest ecosystem, it's a bit complex. Like over the past 10 or 20 years, there was like a lot of different policies ongoing, and also different disturbance events or climate extremes or hazards ongoing. So if I would really like to understand multi-stress and multi-policy and attribute them in a quantitative way, do you think it's also possible from some of the causal inference, or you think that would be a bit difficult?
Yeah, it's a great question, right? Because so often in environmental sciences, it's not as, we're seeing in maybe health policy, right? Like this one policy at a certain point in time, you have, something happened here, this policy was enacted here, and, it's maybe heterogeneous over space. So one thing I will kind of note that your question brings to mind is there's a researcher, Zhao Wu, who also came out of the same group at Harvard, but is now at Columbia, has done kind of similar work thinking about adapting causal inference methods to this environmental sciences setting. And he wrote a paper, I think it was Science Advances, looking at impact of prescribed burns on kind of the risk of wildfires later on. And that was a case where he basically kind of was clever in defining what the treatment was. So he was basically looking at, okay, has there been a prescribed burn, but then was defining the treatment as kind of then like the time since the burn. So it was a way in which, you could have prescribed burns that happened at different times in different places across the Western US or California. But he was kind of clever in the way that he defined the exposure to then be able to do kind of one pooled analysis. So I don't know if that would be applicable to your setting because you're talking about maybe like different types of policies or different types of events, but that would maybe be the direction I would take if you wanted to apply some of these causal inference methods in that sort of setting is how could we maybe be creative in defining what the treatment is and some way of basically kind of enabling harmonization across time periods or across different types of policies. Does that answer your question?
Yeah, definitely. The paper that you mentioned, is there any way to get that one?
Sorry, you're asking for the citation?
Yes, right.
Okay, yes, I'm happy to send that. Maybe I'll continue the discussion, but I can send it to Casey or Becca after the talk.
That sounds really great. Thank you very much.
Okay, yeah, thanks for the question. Anything?
You should be a little more casual.
Okay.
Ask
Yeah.
all your questions, but thank you again.